It is well established that the Earth and all of the planets of the solar system orbit around our star, the Sun. We know this thanks to the tireless work of scientific heroes through the ages, such as Copernicus, Kepler, and Galileo, each of whom helped revolutionize our understanding of the cosmos with the heliocentric model of the solar system. With this in mind, one may be curious if indeed the Sun itself orbits some other, more massive object in turn, and the answer to that question is a resounding yes. Ahoy! Welcome aboard our little spaceship. This is your captain, Star-Lord, speaking. Today we'll be traveling to the center of our very own Milky Way galaxy to take a look at one of the most extreme and most powerful objects in the known universe. A supermassive black hole. Computer, prepare for jump. Lock destination, Sagittarius A star.
Aye, sir. Locking in destination. Designation, Sagittarius A star. Brace for jump sequence in 3, 2, 1. Jump commencing. Jump completed. We have arrived at the destination.
Thank you, computer. Bring up visuals on the main screen, please.
Aye, sir. Now viewing Sagittarius A star.
Perfect. Isn't it beautiful? That right there is Sagittarius A star, the supermassive black hole at the center of our galaxy. And when we say supermassive, we're not kidding, folks. This bad boy is rocking more mass than 4 million suns combined, all condensed into a small enough space that if it replaced our sun at the center of the solar system, the event horizon wouldn't even reach past Mercury's orbit. This black hole gets its name from a typical astronomical naming convention of the time. The A denotes the location as the brightest source of radio signals in the region of the Sagittarius constellation, and the asterisk at the end, commonly read as star, was added to specify the compact source of the radio emissions, aka the black hole, that was not quite as bright as the whole of the Sagittarius A region around it. After all, there's more than just a monstrous black hole here. Orbiting relatively close to this gravitational heavyweight are a number of daredevil stars. Make no mistake though, over 99% of the mass of our galactic center belongs solely to that awesome, supermassive black hole. Now you might imagine such a black hole like you might imagine a giant whirlpool, quickly sucking in everything around it until there's nothing left, right? Well, the reality is quite different, believe it or not. While black holes definitely do their fair share of sucking, they still behave according to their mass, just as all other celestial bodies do. That means that it is entirely feasible for objects like stars to swoop in for a pretty tight orbit around a black hole's event horizon, granting that the object has sufficient velocity to zoom back out of that oh-so-steep gravity well. And boy, oh boy, do these stars zoom. Named the S-stars, these solar speedsters reach speeds of up to several percent that of light itself. The fastest among them rocket by at up to 24,000 kilometers per second. For reference, the Parker Solar Probe, billed as the fastest object ever built in 2023, reached a relatively paltry maximum speed of just 177 kilometers per second as it made its then closest approach to the Sun. Speaking of the Sun in orbits, let's talk about the whole reason we're here. What is it that the Sun orbits? As you may have guessed by now, the Sun, as with virtually everything else in our galaxy, is orbiting around this incredibly volatile central region, Sagittarius A. Notice I did make the distinction that the galaxy orbits around Sagittarius A, not Sagittarius A star. That's important to note. While this black hole is indeed a behemoth that exerts its gravitational influence on a wide space around it, that effect diminishes very quickly beyond its own region of space, implying that a galaxy's components do not orbit the way they do, simply because of the supermassive black hole at its center. To be perfectly honest with you, we're not entirely sure why galaxies rotate the way they do. Not that we don't have some pretty solid theories, of course, ranging from dark matter galactic halos, all the way to modifications of traditional Newtonian dynamics. So, everyone knows what our galaxy looks like from a glance, right? I'm betting you've all seen our Milky Way galaxy represented like this before. Except, oh wait, that's not the Milky Way, is it? How about this one? Yeah, that's our beautiful Milky Way. Probably. If you didn't catch on to which image was our galaxy right away, don't worry. No one has ever been able to image our galaxy because of the simple fact that we're inside of it. Galactic dust and gas clouds, densely packed sources of starlight, and more all block our view of the galaxy, and indeed much of the universe, since many types of light are absorbed by these obstructions before they even reach us. Luckily, we can still see some things through the Milky Way's obstruction via a clever collection of wavelengths of light outside of the visible spectrum, such as infrared light. And before anyone asks, nope, there's no way we can send a probe outside of the galaxy to image it. For starters, even getting to the nearest edge of our galactic plane would take the fastest probes dozens or even hundreds of millennia with perfect conditions, and they still wouldn't be able to image the whole thing for another few million years at least. That being said, we can take a look at all the other galaxies around us, of which there is certainly no short supply, and compare them against our own galaxy to get an idea of what it should look like. Our species spent hundreds of years struggling to understand the shape of our own galaxy, the cosmic quest truly beginning in the 1700s with Thomas Wright's anachronistically clever supposition that we lived in a flattened galactic disk of stars among many other galaxies. Dude was way ahead of his time, eh? Immanuel Kant is famous for having been enraptured by this idea of island universes, but many of his peers wrote it off entirely. Some of them were still trying to prove the sun was the center of the universe. Well, Edwin Hubble finally proved, once and for all, that Wright was, well, right, by measuring some of the variable stars in the then named nebulae and finding that they were much, much too far away to be in the Milky Way. He used variable stars because they pulsate quickly, making them fairly precise, distant markers. Of course, many of Hubble's peers were critics of this idea too, including Harlow Shapley. Shapley was pretty smart, formulating the idea of the stellar habitable zone and even measuring the size of the Milky Way using the same method as Hubble, Cepheid variable stars. But he, and others like him, had a lot of trouble accepting that we lived in just one galaxy among countless others. Shapley even famously debated Hubble on the matter publicly. To give you an idea of when this was occurring, Einstein had just published his theory of general relativity a few years prior, in 1915. Big credit to Shapley, though, for being a true scientist, because as soon as Hubble showed him the data, Shapley immediately recanted his stance and became a believer. From that moment on, the work to identify the exact shape of the galaxy could truly begin. We now know, from decades of extensive observation, that our entire solar system is an invisibly small speck in a minor galactic arm, jutting off of one other massive galactic arm, which is itself just one of a number of arms spiraling around a central galactic bar. Let's start with the number of arms. While it can be difficult to determine at first glance how many arms there are, we can see that there are two major arms, as expected from a barred spiral galaxy: the Perseus arm, where the Sun and Earth are roughly located, and the Scutum Centaurus arm. Other lesser arms do appear in observations, however, such as the Norma arm and its outer arm, as well as Sagittarius arm. And even though we're technically in the region of the Perseus arm, more specifically we're located in a smaller arm, named the Orion Spur, that seems to overlap some other arms. It's hardly big enough to be an arm on its own, but it does have many of the hallmarks of one. That's not even going into the near and far 3 kiloparsec arms, or that extra long arm extension that seems to cause the Norma outer arm to spiral around the entire galaxy. Eesh. And you bet, all of it orbits around the galactic center, home to that monstrous black hole Sagittarius A star. Well, we've reached the end of our trip to the center of our galaxy today, and boy has it been an impressive sight to behold. But it's also opened up another mystery that still keeps astronomers awake at night, to this very day. You know how I mentioned those galactic rotation curves don't exactly match up with theoretical predictions, meaning the outer edge of our galaxy is rotating a bit faster than it should? Well, a distributed dark matter halo around the galaxy is just one solution that, like the final puzzle piece of a cosmic puzzle, seems to fit perfectly. But it's not the only workable theory going around. Turns out, modifying the very basis of classical physics just a bit also seems to solve the rotation curve mystery, as well as a few other cosmic mysteries. Well then, with that in mind, it's time. Let's get ready for our next exploratory mission, to answer the question of why galaxies rotate the way they do. Join me on that video by clicking the thumbnail linked on screen now. I'll see you over there. Computer, prepare for jump. Lock destination, the Norma outer arm.
Aye, sir. Brace for jump sequence in 3, 2, 1. Jump commencing.
If you enjoyed this video, don't forget to leave a quick like and subscribe to the channel if you want to see more about space, science, and all that good stuff. Thanks for watching. I'll see you on our next trip.